Let's get started with this review for exam number 2. That includes chapters for electrostatics, the electric force chapter 22, then electric field chapter 23, then chapter 25 for electric potential, and chapter 26 for electric potential and electric field. So let's get started with this problem, which is not 19 in chapter 22. So as you can see there is 3 charges located in a triangular configuration. There it's an equilateral triangle. All the sides are 1 centimeter. I'm going to label the charges Q1, Q2, and Q3, and they're asking us to calculate the force on Q1, the one located at the top. All right, so we're looking for the net force acting on Q1, and the net force is going to be the sum of the force that charge number 2 puts on charge number 1, which should be in that direction, located along the direction of the vector is along the line that connects the 2 charges, and it is pointing, it's acting on Q1 away from Q2. This force is repulsive, so Coulomb's law tells us that it should be in that direction. So this is the force that charge 2 is putting on charge 1. But that's not the only force. We also have the force that charge 3 is putting on charge 1. Again, you should draw it along the direction of the line that connects the 2 charges, 3 and 1. And it is also repulsive since those 2 charges have the same sign. They're both positive. So these are the 2 forces acting on Q1. So we're going to need to add those forces. Remember that these are vectors. You cannot just simply calculate these 2 numbers and add them like they were just regular numbers. We have to find the components of these vectors and add the vectors component by component. So to start calculating components, it's important to notice that this angle here that F21 makes with the horizontal line is also 60 degrees. Because the angles for this equilateral triangle, every angle is going to be 60 degrees, so this is also 60. The base of the triangle and the horizontal line that we just drew are parallel, and we have a common line, so the angle is 60, which is the same as that angle. All right, for F31, same reasoning applies, and the angle that F31 makes with the x-axis should be also 60 degrees. All right, let's calculate the magnitude of the force that 2 puts on 1. Having the magnitude and having the angle, we're going to be able to find the components, the x and the y components of that force. We'll do the same for the F31, and then we add x component with x component, y component with y component. So, magnitude of the force that 2 puts on 1. So according to Coulomb's law, it should be K, the electrostatic constant, Q2 times Q1 divided by the distance between the 2 charges squared. All of these charges are positive, so this is going to give me a positive number, which corresponds to the magnitude of the force. The direction, I already have it. The vector, I already have it in the figure, so I just need to calculate the magnitude. So the magnitude of the force that 2 puts on 1 is going to be equal to the magnitude of the force that 3 puts on 1, and that's only because the charges at the bottom are equal to each other. Notice that Q2 and Q3 have the same value of 2 nanocoulombs. So the force that each one of these charges puts on Q1 is going to be the same. There's no other reason why it should be the same. It's just because those 2 charges are the same. So what is the magnitude of this force? So the electric constant K, 9 times 10 to the 9, we're multiplying by charge Q2, which is 2 times 10 to the minus 9. Remember that n, lowercase n, before the C means nano, so 10 to the minus 9, so 2 times 10 to the minus 9 coulombs. We're multiplying by the charge Q1, which is 1 nanocoulomb, and that's what goes in the numerator, or Coulomb's equation, and the denominator is going to be the distance between 1 and 2. So charge 1 and 2 have a distance between them of 1 centimeter. You cannot just put a 1 there. Remember that we have to calculate everything in MKS or SI units. It's the same thing. MKS stands for meters, kilograms, seconds. which is the same as to say that we're using the international system of units. That's what we do in physics and in all of science. So meters is the appropriate distance quantity, so not centimeters. So 1 centimeter is 10 to the minus 2 meters, and you need to square that in the denominator. Notice that I'm very much aware that I have to use MKS units, so every quantity that I put in my formulas is going to have the appropriate or use the appropriate conversion factor if it's needed. And I'm going to skip writing the units because, like I said, I'm going to be paying a lot of attention to having the correct units to begin with. So I know that as a result, this number that I just going to calculate is going to be in newtons, which is the international system of units for force. All right. So plugging in the numbers, 10 to the minus 9 and 10 to the 9 and 10 to the minus 9 are going to cancel. We got a 9 times 2, which is 18. We got a 10 to the minus 9, and then we have a 10 to the minus 4 in the denominator. You end up with the answer 1.8 times 10 to the minus 4 newtons. This is the partial result for the magnitude of the force that charge 2 puts on 1, which is also the same as the magnitude of the force that charge 3 puts on 1. Both of them are 1.8 times 10 to the minus 4 newtons, and the direction of those forces is already indicated in the picture. So we have these two forces, they're identical in magnitude, the directions are shown there. How do we add these two vectors? The net force vector, as you can tell, is going to be pointing straight up. That's because the magnitude of those forces is the same, the angle with the horizontal axis is the same, so the x component of one force is going to cancel the x component of the other one. That should be clear for you. So no x component for the net force. The net force is going to be straight vertical. For the vertical component of the net force, we're going to have 2 times the vertical component of one of these forces. The magnitude of one of the forces is F, which we just calculated. I'm going to replace it in a second. Is 1.8 times 10 to the minus 4. And then we're going to multiply by the sine of 60 degrees to get the vertical component. And we have 2 of them, so that's why the factor of 2. And to put it in vector notation, this is going to be going in the vertical direction, so we indicate that with a vector, unitary vector j hat. So put it in the numbers, so factor of 2 times 1.8 times 10 to the minus 4. The sine of 60 degrees is 0.866. So plug that in, and you get 3.1 times 10 to the minus 4 newtons. And the direction is up because we only have the unitary vector j hat left. So this is the magnitude and the direction of the net force acting on charge number 1. So that's our answer for this problem. All right, the next problem has 2 parts. So what we have here is 2 charges. As you can see, both are positive, but one has 4 times the amount of charge of the other one. The ticks are separated equally, so that we can use that as a unit of distance. And what we're looking for is to draw a dot on the figure, on the x-axis, at a point where the electric field produced by these 2 charges would be 0. Where on the x-axis is the electric field 0? All right, so to start working on this, let's pretend that the little charge is not there. So what would be the electric field produced by the big charge? Well, you know that the electric field produced by a positive charge points away, so any point that you consider, any point that you want to look at would have an electric field. Any point that you look at is going to have an electric field pointing away from the charge. You can draw a line and it should be pointing away. So in particular on the x-axis, which is what we're interested in, the electric field produced by the big charge is going to be vectors pointing to the right when you are to the right of the big charge, and the vectors electric field would be pointing to the left at the points where we are on the left of the big charge. Now, if we look at what should be the electric field produced by the small positive charge, when we have it, then we have a similar situation, of course. Any point on the x-axis that you select is going to have an electric field produced by the little charge that would be pointing away from the little charge. So notice that in some regions the electric fields are pointing in the same direction, the black and the red. The electric field of the big charge and the electric field of the small charge are pointing in the same direction, and in other points. So in this region, for example, you can see that the red and the black arrows are pointing in the same direction, so the two electric fields are going to add up, so they're never going to cancel each other and give us a 0, which is what we're looking for. So this is not the place where the electric field is going to be 0. In the middle, that's where we could find the electric field being equal to 0, because notice that the electric fields are opposite each other. If we think back to the analogy of positive charges as blowing out air away from them, this invisible electric wind that I was talking about, then each charge is blowing air in opposite directions, so these two opposing electric winds can cancel each other. So that's the place, in that region, we're going to find the electric field. In the other region, on the left of both charges, notice that the electric fields, one more time, they add up, and therefore they will never cancel. So the region or the place where the electric field is going to be 0 is going to be somewhere between the two charges. The question is where exactly. So let's focus on that. We know where, or the region where this should happen. Now exactly where. So we're gonna look at the middle point, from the midpoint between the two charges to the left. So I'm wondering if the electric field would be 0 in that region, or would it be 0 in this region? So if you look at the region on the left of the midpoint, you'll notice that you would be close. If you evaluate the electric field produced by the big charge, then you're close to that charge, and that charge has the biggest charge, 4 times as big as the other one. So that charge will produce a strong electric field, the one that I mark here with an E1. For E2, the electric field produced by the small charge, notice that you are further away from that charge than you are from the big charge, so that affects the electric field, and on top of that you have less charge. So to the left of the midpoint, there's no way those two vectors could cancel each other. You would expect that E2 is always going to be less than E1 anywhere in that region. So that's not where we're going to find the A equals 0 point. So it must be in this region, from the midpoint to the right, in between the charges we already said. So, but exactly where? So there should be a point where the two electric fields are equal in magnitude. We already know that they will be pointing in opposite directions. So now we need to figure out the point where the magnitudes are the same. So at this hypothetical point that we're trying to find, the distance to the big charge, it's x2. I guess I should have called it x1 since I called this one E1. Yeah, let me just change this to 2 and this to 1. Sorry. So x2, the distance to the big charge, I'm going to call it x2. The distance to the small charge, I'm going to call it x1. We know that for certain values of x2 and x1, for a particular value, E1 should be equal to E2. So what does the equation for a point charge say that the electric field should be? So the electric field of charge 2 should be kq2 divided by x2 squared. And since the two electric fields are equal at that hypothetical point, then kq2 over x2 squared should be equal to kq1 over x1 squared. The k's are cancelled, it can be cancelled, and you can divide the charges on the left and have the distances on the right, and you get q2 divided by q1 equals x2 over x1 squared. Now we know that q2 is 4 times q1, because the picture shows us that, 4 pluses instead of 1, or compared to 1. So the ratio on the left is 4, so we know that the ratio of the distances squared is 4, which means that x2 compared to x1 should be 2. So x2, let me just slow down there, x2 is equal to 2x1. Now at this point you could probably figure out already what are the distances, because we have, we're looking for the x2 numbers, x1 and x2, such that one number is twice as big as the other number, and also that the sum of the two numbers is equal to 3, right? Because the distance between the charges is 3 units, 1, 2, and 3. You can count 1, 2, and 3. 3 units is the distance between them. So two numbers that add up to 3, and one number is twice the other. That is pretty simple. The answer is 2 and 3. 2 and 1. So x2 should be 2 and x1 should be 1. If you don't see it clearly, just use the equations. You have two equations. You have this equation. The sum of the x's, x2 plus x1, is the distance between the charges, which is 3, and x2 is supposed to be 2 times x1, so a bit of algebra gives you the answer. x1 should be 1, x2 should be 2. All right, so we found that point where the electric field cancels. That point is going to be right here. 2 units away from the big charge, 1 unit away from the small charge. All right, we have a part B for this problem, which is similar to the previous one, except that the small charge is now negative. So we're back to trying to figure out in what region and exactly where the electric field should cancel out. So the electric field produced by the big charge on the left side of it is pointing to the left, away from it. The electric field produced by the negative charge, which I'm drawing with a red vector, should be pointing towards the negative charge. That's a characteristic of the electric field of positive and negative charges. For negative, it points towards it. So in this region, the two electric fields are not going to cancel out. Even though they have opposite directions, they will not cancel out because in that region, you're closer to the stronger charge. So the electric field not only has a big charge, or the electric field produced by the big charge, if you think of the expression, it not only has a big charge in the numerator, but it also has a small distance in the denominator. So that electric field, this electric field produced by this guy, is always bigger than the electric field by the little charge. So there's no way they would cancel in that region. You're always closer to the bigger charge. For the region in between them, the electric field produced by the positive charge points to the right, away from it. The electric field produced by the negative charge, somewhere in between them, points towards the negative charge. So that results in the two electric fields pointing in the same direction, therefore they never cancel. And the last possibility is the region on the right of the negative charge. So in that region, the electric field of the positive charge points to the right, away from it. The negative charge is sucking in the electric wind, so the electric field points towards it. And those two fields are in opposition to each other. And we have hope that those two electric fields cancel each other because in that region, you're closer to the weaker charge. So the effect of being closer to the negative charge means that you could compensate for the negative charge being smaller in magnitude than the positive charge. So this is where we're going to find the electric field being equal to 0, but where exactly do we find that point? So again, let's choose some point, call the distance between the point that we think that the electric field is going to be 0 and the negative charge. I'm going to call that distance x1. The distance to the positive charge, I'm going to call it x2. And too fast. We know that the charge 2 is 4 times the charge 1 in magnitude. One is positive, the other one is negative, but in magnitude is 4 times. And we know that the electric fields are going to cancel each other, so their magnitudes must be equal. So E2 should be equal to E1. And writing exactly the same equation as we did before, we had KQ1 over X1 squared equals KQ2 over X2 squared, which gives us one more time that X2, the distance between the point on the x-axis and the big charge should be, and big charge, which is X2, should be twice the distance to the small charge, the negative charge. So we're looking for a point on the x-axis where the distance to the positive one is twice the distance to the negative one, knowing that the distance between the charges is 3. So I think you can probably already see that, what's going to be the answer to this, or the solution to this. We should be at a point in the x-axis where the distance to the positive charge is 6, because that will place that point 3 units from the negative charge, and clearly 6 is twice 3, so it matches the condition x2 equals 2x1, and that should be our answer. That's the e equals 0 point. Again, if you don't see that clearly, then just do the math. Call that distance x2, the other one is x1. We know the distance between the two charges is 3 units, so in equations we have x2 equals 2x1, and the other equation is x2 minus x1 equals 3 units. x2 minus x1 equals 3, so that's your second equation. You have a system of two equations with two unknowns. The second equation is x2 equals 2x1, and you solve for them. Replace, instead of x2, write 2x1, so you get 2x1 minus x1 equals 3, therefore x1 equals 3, and x2 must be 2 times that, so it's 6. So just what we said before. All right, so we have identified the point where the electric field is 0 in this situation. It should be 3 units to the right of the negative charge. All right, that's it for that problem. Let's do one more and then we take a break. So in this one, we're looking for the strength and the direction of the electric field at the point indicated by the dot in the figure. So there is a rectangle there, charges at the corners, and we are looking for the electric field at that position. We want the electric field in component form. That means the electric field written as a vector with the Ex times I hat plus Ey times J hat. Ex is called the X component of the electric field, Ey is the Y component of the electric field. So first calculation is for the components, and the second calculation is to give the electric field as a magnitude and a direction, an angle from the positive x-axis, clockwise or counterclockwise. All right, let's get started with part A. First of all, let's label the charges that we have here, Q1, Q2, Q3. Each of these charges is going to produce an electric field at the location shown. So we're gonna the charge Q1 produces an electric field along the line away or connecting the point with the charge, and it's away from charge Q1 because it is positive. Charge 2 is going to produce an electric field pointing towards it because it's a negative charge. The electric wind points towards it, so that's the direction of E2. And charge 3 is going to produce an electric field away from it at the location indicated. So those are the three vectors that we need to add to find the net or the final or the net electric field. So this is what we need to do, add the three vectors. So let's start with the first vector. Let's write E1 in terms of its x and y components. So as you can see from the picture, E1 is a vector that is straight down. So E1 only has a y component, and the y component should be negative. Of course, it's pointing down, so negative. The magnitude of that component should be the magnitude of the vector, and the direction is specified by the vector j hat. All right, now what's the magnitude of that electric field? So for a point charge, it's k q1 over the distance square. So q1, so k is 9 times 10 to the 9. Q1 is 10 nanocoulombs, so 10 times 10 to the minus 10 times 10 to the minus 9 coulombs, and the distance is r1 is, as you can see there, 4 centimeters. So again, I'm writing 4, not just 4. We have to write it in meters, so 4 times 10 to the minus 2 meters, and that goes square. Again, I made sure everything is MKS, so I'm going to skip writing the units. So just plug in the numbers in your calculator. 10 to the 9 and 10 to the minus 9 cancels. 90 divided by 16 in the denominator, and the answer is 5.625 times 10 to the 4 newtons per coulomb, which is a unit for electric field. But you also learned that volts per meter is also a valid unit for electric field. So either one. I'm just going to stick to newtons per coulomb. So written as a vector, we have that the E1 vector is minus 5.625 times 10 to the 4 newtons per coulomb times J hat. All right, moving on to the electric field number 2. So the electric field number 2, we know in what direction it's pointing, is along that diagonal of the rectangle. We need to find the angle theta 2 so we can compute components. So the tangent of theta 2, as defined in my picture, is the opposite side, which is 4 centimeters, divided by the adjacent side, which is 2 centimeters. And the tangent of theta 2 is therefore 2. And using the function inverse tangent of 2, you get 63.43 degrees. So that's the angle theta 2. So the electric field vector E2 should be, notice in the x direction, it's going to be minus the magnitude times the cosine of angle theta 2. That will be in the x direction. Why the minus? Because the x component, as you can see, when you project on the x-axis, the shadow of E2 is pointing to the left, so that's a negative x component, and projecting it down to the x-axis goes with the cosine of the angle. All right, so that's the x component. For the y component, we're going to need to project on the y-axis, so it will be E2, the magnitude of E2, times the sine of theta 2, and that goes in the j hat direction. We're expecting a positive y component. All right, what's the magnitude of the electric field vector? It's k times the charge, the absolute value of the charge. Again, we don't need to put a minus here because we're already knowing what direction the electric field is, so we just need to compute its magnitude, and with the angle we'll be able to figure out the components. So plug in Q2 absolute value, which is 5 nanocoulombs. The distance R2 is the distance along the diagonal. So that distance along the diagonal square is what we need in the denominator. It's R2 squared. So we don't need to take any square root here, and we can use Pythagoras theorem that says the hypotenuse square equals the adjacent side square plus the opposite side square. So adjacent and the opposite lengths are given there. It's 2 centimeters and 4 centimeters. Again, don't forget to convert to meters. And that's R2 squared, which we're gonna plug it in the denominator. We're gonna get, for R2 squared, we're gonna get 20 times 10 to the minus 4, and the units should be meters squared. All right, so we're ready to replace the numbers to get the magnitude of E2. So K is 9 times 10 to the 9. Q2 in absolute value is 5 times 10 to the minus 9 because it's nano coulombs. And the distance squared in the denominator is 20 times 10 to the minus 4. Everything is MKS. Our answer should be newtons per coulomb. And we get 9 times 5 is 45 divided by 20. And 10 to the minus 4 goes to the numerator as 10 to the 4. The final answer is 2.25 times 10 to the 4 newtons per coulomb. Well, that's not the final answer. That is the magnitude of the electric field 2, E2. So now we have to plug in the magnitude of the electric field here and here to be able to figure out the components. So the x component is minus 2.25 times 10 to the 4 times the cosine of 63.43. That goes in the x direction, so I hat. And the y component is the magnitude of the electric field, which is 2.25 times 10 to the 4, but we need to multiply by the sine of the angle, 63.43, and that goes in the j hat direction. So our final answer for the electric field 2 is approximately minus 1 times 10 to the 4 I hat plus 2.01 times 10 to the 4 j hat. All right, one more vector to go. We need to calculate E3 before we can add all of these vectors together. So let me clean up a little here. All right, so E3, notice that is straight on the x-axis. So it only has it can be written as a magnitude of the vector times the I hat vector, unitary vector. So the magnitude of the electric field E3 is 9 times 10 to the 9. The charge Q3 is 5 nanocoulombs, so 5 times 10 to the minus 9, and the distance is 2 centimeters. Well, the distance between Q3 and the point where we're measuring the electric field is 2 centimeters, so that goes like 2 times 10 to the minus 2 and square. So plug in the numbers, cancel things, and you get 11.25 times 10 to the 4 newtons per coulomb in the I hat direction. So that's our answer for the electric field E3 vector. So now we're ready to write the final electric field in X and Y components. So we're looking at the X components here. So everything that has an I hat, we're going to add it together. So in this case, we have 11.25 and minus 1. Those both times 10 to the 4. So those are the only two terms with I hat. So 11.25 minus 1 is 10.25 times 10 to the 4 newtons per coulomb in the I hat direction. Now we take care of the J hat terms. So we have two terms, J hat. One is negative minus 5.625. The other one is 2.01. So minus 5.625 plus 2.01 gives you minus 3.61 times 10 to the 4. And that is in the J hat direction, newtons per coulomb in the J hat direction. So we have both the X and the Y components of the net electric field. So that's the answer for part A. The last part B, is to find the magnitude and the direction of this vector. So having a vector in components allows you to calculate the magnitude and the direction of the vector. So the magnitude of the vector, Pythagoras theorem says is the square root of the X component square plus the Y component square. You put in the components. Notice that the minus 3.61, you don't need to write a minus sign there because the minus goes inside the square. Inside that parenthesis where I put 3.61, in principle you should put minus 3.61, but this thing is going to be square, so it doesn't change anything to put a plus or a minus there. Some people make a mistake, very basic mistake, of putting the minus outside. Putting the minus outside. That would be wrong. What you're putting is the X component squared plus the Y component squared. If the Y component is negative, you put the minus inside. The minus inside this parentheses and then you square it, doesn't matter, becomes a plus. So never put that minus sign outside. Alright, so what is the final answer? Putting the numbers in the calculator. The electric field magnitude is 1.09. You could round out to 1.1 times 10 to the 5 newtons per coulomb. And the angle is the last thing to do. So the angle, as you know, to find the direction of a vector, you take the inverse tangent of the y component of the vector. In this case, the y component is minus 3.61. And you divide it by the adjacent. Inverse tangent of opposite divided by adjacent, or y component divided by x component. So the x component is 10.25. So divide those two numbers, take the inverse tangent of that, and the answer is that the angle is minus 19.4 degrees. That's a perfectly valid answer for the angle. The problem is, however, specifying that you specify the angle as measured clockwise or counterclockwise. So before we do that, actually, sorry, this is important. So when you get an answer for the angle of a vector, always check to see if it makes sense. Where is, according to the answer that the angle is minus 19.4 degrees, where is the net electric field? It should be in the fourth quadrant, because that's a negative angle measure from the positive x-axis, and check to see if that is consistent with the sign of your components. So if the vector is in the fourth quadrant, you're expecting the x component to be positive and the y component to be negative, and that's exactly what you have. So the calculator answer is correct. Remember that the calculator might not give you the right answer when you use the inverse tangent function. You always have to be alert and double check. If the answer is not correct, all you have to do is add 180 degrees, which is not what we're having to do here because the answer from the calculator is correct. The expected net electric field is in the fourth quadrant. I was saying that you always have to read carefully what the problem wants, how the teacher wants you to write the answer. So here they're saying that we should specify the direction as an angle measured clockwise or counterclockwise from the positive x-axis. So an angle of minus 19.4 degrees is an angle of 19.4 degrees measured clockwise. Alright, so that is the final answer for that direction. Alright, I'm going to stop this video here and make another one with some more problems.